award, Mirko Tribastone and Andrea Vandin. And this work originates essentially by observing that a lot of high-level formalisms like process algebra, Petri nets, chemical reaction networks, electric circuits, queuing networks, and Markov chains have ordinary differential equations, short ODEs, as semantics. And this brings us to the idea of introducing directly a language for ODEs. So instead of working on many high-level formalisms that induce at the end of the day ODEs, we want to work on a language which treats ODEs as first-class citizens. And we will elaborate on this idea by using on the example of chemical reaction networks, in particular on this chemical reaction network given here by those 5 reactions. So if we are given this guy over there and we apply the law of mass action semantics, we will end up with this ODE system, which is given essentially by 5 ODEs. On the right-hand side, A refers now to the concentration of A, whereas B refers to the concentration of B. Dot means the change of the concentration of the species with respect to time, which means essentially that the change of A is given by the minus of the concentration of A and minus of the product of the concentrations of A and B. So what we now propose is to define a language for defining directly the drift which we have here. And we call our language intermediate drift-oriented language, short idle, which is given by a 2-level grammar. The first level grammar allows us essentially to define the ODE, and each ODE is concatenated by means of the comma operator, which is suppressed here. And the second level defines us the drift. So I don't want to go into details on the drift, but let me just stress that the grammar is, although it's quite concise, it's very expressive. So we can encode all the high-level formalisms from the last slide, but also more. So for instance, we can capture Hill semantics because we can capture rational equations and truth terms. Okay, and if we have constructed ODE, then what we do is we fix initial concentrations. So it is the concentration of the species at time point 0. And now if we apply the drift semantics, we can evaluate the trajectories of the ODE system. Okay, so having set up the scene by defining the language for ODEs, what we want to do next, we want to argue about idle programs, that is about ODEs. And we want to argue about those guys by using 2 established techniques from the field of ODE systems. The first one is called backward differential equivalence, and I will explain it briefly on our running example. So it is based essentially on the fact that, okay, let us assume that at time point 0, we initialize A and B equally. So A and B are equal at time point 0. Then if you replace now B, each B here by A, you will rewrite this term into the same term as this term. Which means essentially that if you start your ODE system, this ODE system, in the case where A and B have equal values, then the trajectories of A and B will coincide. Consequently, if you replace any B by A and drop this redundant ODE here, we can solve this ODE system by solving the smaller ODE system. And the idea is, again, that we say, okay, we can do this only in the case where A and B are initialized equally. But if we initialize them equally, then the traces will be equal, which means that A and B will be equal at all time points. And because of this, we call this partition where A and B are essentially in the same block, BDE. So the intuition is, again, if the guys are in the same blocks, then they have the same trajectories. Okay, so this is a rough idea behind BDE. And now what we want to do, we have now our idle, and now we want to express this BDE in terms of idle. So the first message is that we can encode BDE in a logical formula which uses idle terms. And in particular, what we can do is, given a partition H, calligraphic H, we can decide whether this partition is a BDE partition or not by checking whether this formula is true or not. And the intuition behind this formula is quite easy. Here you say, well, whenever the guys in the same block have the same value, then they should have also the same drift. And this is quite intuitive, quite reasonable, because remember, the guys in the same block have the same trajectories. If they have the same trajectories, they have the same derivatives. And the derivatives are nothing else than the drifts here. So you see already that BDE implies this, and you can also show that this formula implies BDE. So what is nice about this formula is the fact that it's quantifier-free, meaning that we can invoke a satisfiability model theory solver to check whether a given partition H is a BDE or not, which is great and nice. But at this point, we somehow assume that we are given an H. So we have somehow, if we want to relate to idle programs, we need to have an intuition behind the relation between them. So we need to come up with the H. And the next step would be to say, assume that we are given an idle program, and we want now to calculate a smaller idle program that is related to the original idle program by means of the BDE notion. So this, speaking mathematically, can we calculate the course's BDE partition, for instance? And the answer is yes, we can calculate the course's BDE partition by using a partition refinement algorithm that we will now present on the next slide. The next slide is quite dense, but we will go step by step, so don't worry. So first of all, we just copy-paste the formula which characterizes BDE from the last slide, nothing new here. And here we have now the main algorithm, which invokes an auxiliary function which is given here. Don't look at this, look just at this. The idea here is the following. The input parameter to this algorithm is a partition G, which is arbitrary. And what this algorithm has now to calculate is the course's BDE partition that refines the partition G. The idea behind this input G is that we want to allow the modeler to give some constraints. The modeler should be able to say, I don't want to put X and Y into the same block. And if we come up with a partition G where X and Y are not in the same block, then the course's BDE partition that refines G will have this property as well. Okay, so informally, G is can be seen as a set of constraints that we want to impose on the calculation, impose on our algorithm. And now we take a look at the algorithm itself. And it's actually quite easy because it's a while loop, but it calls the refine function until it cannot refine anymore. Because if H prime is equal to H, then we return H, and that's it. Instead, if it's not H, that is, if it's really a proper refinement of H, then we replace H by H prime and go again into the loop. And now we turn to the actual meat of the algorithm, which is essentially the refine function. So, and here we now apply the SMT solver. The first step is, given a partition H, we ask, is it a BDE partition or not? If it is a BDE partition, then the SMT solver, we simply return H prime, and then we terminate here, and we are happy. Instead, if it's not a BDE partition, then we let the SMT solver give us an assignment sigma, which falsifies this formula. Because if H is not a BDE partition, this formula is wrong. Hence, we can find an assignment sigma that falsifies this formula, and which means essentially that at all blocks, the variables in any two variables in any block have the same value, but there exists at least one pair in one block which has different drifts. And the splitting algorithm does now a quite easy step. In the end of the day, it's a counterexample driven partition refinement. We say essentially that two guys are told apart by the refine method if they have this different drift, and that's it. And now we do this example. We start here with a trivial partition, that is, we don't make any constraints. We put all the species or variables, if you like, at the same block, and ask the SMT solver, is it a BDE partition? And the answer will be no, it is not, and the possible assignment, sigma, which falsifies it, would be, well, where all the species are set to 1, because then, if you calculate the drift, which will give us essentially the vector -2, -2, 2, 1, 2, we see that A and B have the same drift, so we can put them together, but C and E have a different drift. So they have still the same drift, but they have not the same drift as A and B, so they go in a different block. And D is the only guy which has the drift 1, so it stays on its own. So this gives us the H prime of the first iteration, if you like. Now we invoke again the refine function, check whether this is a BDE partition or not. It tells us, no, it is not, and this sigma falsifies this formula. Now we calculate the drift. Now we see, okay, A and B have still the same drift, so they stay in the same block. But C and E have now a different drift, so we tell them apart. And E stays on its own, and now finally we ask again, and now the SMT solver will say, it's a BD partition, and we are done. So this is essentially completes the discussion of the first ODE notation. How much time do I have? Sorry? Very good. Okay, this completes essentially the discussion of the first notion, the backward differential equivalence, and brings us to the second notion, which is called forward differential equivalence. This notion is also known under the name execlumpability and has been studied since the late 60s. So again, we discussed it briefly on the example, on our running example. And this time we note that if we simply add the ODEs of C and E, we can rewrite this guys into that guys. So we just add these two lines together and observe that we can write it in such a way. And this is quite nice, and we like this because we can factor out C plus E on the right-hand side, which means essentially that we can express the left-hand sides, the derivatives of the left-hand sides can be expressed in terms of the left-hand sides. Because we have A, B, D, and C plus E, and on the right-hand sides we have always A, B, D, or C plus C. Because here we don't have something like D times C. This would be not nice because we wouldn't have C on its own on the left-hand side. We have just C plus E on the left-hand side. So the bottom line of this discussion is that if we can solve if we solve this ODE system, we can recover the sum C plus E and the values A, B, D of the original ODE system. And because of this, we call this partition FD partition. So in the case of BDE, the guys in the same block have the same trajectories. Here instead, the guys in a block are essentially summed together. Okay, so, and now we make the same discussion about the FD as BD. So this we want to express it in terms of our language. So I don't have the time to go in with the same level of granularity here, but the point is the following. First of all, there is a nice characterization of FDE, and the nice thing is that this characterization of FDE can be expressed as in a quantifier-free formula, which means essentially that given a partition H, we can check by using again an SMT solver whether this partition is FD or not. However, the bad news is that this characterization, this formula, does not tell us how to split the blocks. And the idea is intuitively that we ask the SMT solver, is this formula correct or not? It tells us no, it is not, and this is an assignment sigma which falsifies it. But in contrast to BD, we don't know how to split now the blocks by using this assignment sigma. And it has been the major technical contribution of the paper to provide a binary characterization of FD that allows for a partition refinement algorithm. So I will give a very high-level idea. So assume that you have an arbitrary partition. We fix two arbitrary blocks out of it, and in these two arbitrary blocks, we fix two guys. So one pair here and one pair there. Two arbitrary pairs, arbitrary blocks. And now what we start to do is we start to move the mass from one variable into the other. So think about the example from the last slide where we had C and E. What we do now is essentially, so we have C, E, and nothing else. So this is just a block of two guys. We move the mass from C into E. And what should now hold is that by moving this mass from one guy into the other, the drifts, the aggregated drifts, so the left-hand sides of this aggregated model do not change. So in terms of the example from the last slide, if we move the mass from C into E, C plus E dot shouldn't change. And this has now to hold for all blocks and for all pairs. If it's closed under this binary mass movements, then it's an FDE partition. And now you can also see why we can do a partition refinement algorithm out of it. Because here we have the notion of pair. If this formula does not hold for some pair, we now can split the corresponding variables. Okay, and this brings us now to the big picture, the takeaway message from the full talk. It's twofold. The first message is, okay, we have our idle language, which allows us to incorporate a lot of high-level formalisms. And then we have the notion of FD and BD, which allows us now to to calculate to reduce an idle program, essentially, in terms of BD and FD, modulo some constraints that are given by the initial partition. This is the first message. Second message, in the past, there were a number of equivalence notions discussed in the context of chemical reaction networks in this Concours 15 and in this BMC systems biology paper, which were sufficient conditions, but not necessary conditions for FD and BD. So they were just implying it, but not characterizing it. And similarly, in the case of this MFCS 15 paper and this Concours 12 paper, there were behavioral equivalence notions for process algebra that were equipped with fluid semantics, that is ODE semantics. Those notions of behavioral equivalence were implying either FD or BD, but they were not characterizing FD and BD. So the second message is essentially that apart from unifying it in terms of the languages, let's say, we unify it also in terms of notions, because now we really characterize FD and BD because it's also now really the mathematical aggregations, not just sufficient conditions for it. And here, last but not least, the number 5 is a classic paper about lumpability of Markov chains. It's stated here because it's a fancy result that you can observe that FDE degenerates to ordinary lumpability on the domain of Markov chains, continuous time Markov chains. And you can also show that BDE degenerates to exact lumpability in the domain of continuous time Markov chains. So we have a sort of uniformization on all levels. Okay, now we have our partition refinement algorithms that is based, that is using the SMT solver. And what we do next is we want to compare the efficiency with respect to the partition refinement algorithms for the sufficient notions from, on the domain of chemical reaction networks from this Concours 15 paper. So, first message is that FDE reduces more than forward by simulation FB, which has been introduced in this Concours 15 paper, and this is because FB is only a sufficient condition for FD. So FB implies FD, but not always. I mean, not any FD partition is also an FB partition. Hence, and this here is an example where we aggregate more. The price, however, is that the specialized algorithm for forward by simulation is much faster than this SMT-based algorithm. The second message is that in the case of BD, we were sometimes faster than the Java implementation, which is quite stunning. And the idea, okay, first, Z3 is very efficient, and second, we have this counterexample-driven partition refinement in the case of BD. This was the algorithm that we discussed. And this fits quite well into this logical form concept of SMT. So this is the explanation why we are sometimes even faster than the specialized Java algorithm. Okay, now future work. I want to leave some time for questions. So, sorry? Okay, so good. So future work, approximate aggregations, which means essentially assume that you are given an ODE drift, but that you cannot really aggregate it because some parameters are not nice enough. But if you change them slightly, you can aggregate. So the question is then, okay, how can you bound the difference between the original ODE system and the perturbated ODE system that can be now aggregated? And if you could bound this in a nice way, then you can come up with a nice approximate aggregation technique. Symbolic aggregation, well, this is because we have an SMT solver, and then a reasonable question would be to say, okay, assume that we don't know certain parameters of our drift, because certain parameters arise maybe from a biological model where something is measured. So the question is, can you assume that we have some freedom in the choice of these parameters? Can we now find some choice of these parameters such that a certain partition becomes BD or FD? And well, the last thing is, as noted before, FD is not that efficient, and one way to attack this point would be to come up with a parallelized algorithm, which would speed up the full calculation. Okay, thank you. Okay, so those benchmarks were chosen from the Concours 15 paper, and the Concours 15 paper used benchmarks from realistic models discussed in Nature paper.